My name is Mark Hoffmann. I study quantum chemistry. Quantum chemistry is part of physical chemistry. And you can ask, what is physical chemistry? I like the definition that G.N. Lewis had. G.N. Lewis, St. Louis, who gave us Lewis dot structures, he defined physical chemistry as the study of anything that is interesting. He was right about Lewis dot structures. I think he's right about physical chemistry also. So the tools of my trade, my instruments, if you will, are pads of paper and computers. And we have a fairly nice set of computers, computer cluster here. This is not the only one in the building, but this is the one that I happen to use. Chemistry. There's a lot of servers. Here we tend to use Linux. There's more of them here. We tend to use Linux workstations and the C computer language. We do parallelization. Sometimes some of these are clustered together, and some of them are standalone workstations. But they're all fairly powerful machines. Probably a little bit more interesting than seeing a picture of a pad of paper. But these are our main tools. So the question then becomes, what do we get out of it? What's the result of our studies? Quantum chemistry, or what is quantum chemistry specifically? And the definition is the application of quantum mechanics to chemical problems. And so the question comes up, well, why do you do that? I mean, what's the use of doing that? And there are many uses, but maybe broad categories, the way I think about it, is that it allows all chemical measurements that you do in a lab need some interpretation. Now, if there's a standard model like bond lengths or that sort of thing, or vibrational frequencies, but what happens when you get something that doesn't follow the standard model? Like, for example, there are some molecules that form pi bonds before they form sigma bonds, usually heavier main group elements. Sometimes you find that you can use the standard model, sort of chemical intuition, if you will, and that works well. But what happens when you can't do that? When you, for example, have a situation where pi bonds are before sigma bonds, you need to figure out a new model, or how the exceptions to the model works. We do some of that. Another thing that quantum chemistry does is help predict molecules that nobody's seen before. So, for example, let's say you want to make something that has specific properties, a certain stability, a certain instability. You might ask, why instability? Well, when you're making a fuel or you're making an explosive, you don't want things to be overly stable, otherwise they don't work. Or something like if you want a certain type of conductivity into it, like a metamaterial which has a thermal conductivity or electrical conductivity of a certain sort. If you can pattern it on something else, you're okay. But if you can't, what do? You call a quantum chemist. Then maybe a third category of types of problems that we look at are problems that involve something that's too fast to observe right now, or too small that you can observe now, or maybe too weak that you can observe now, like coupling of electromagnetic force with a weak interaction, which gives a difference in chirality. But some of these very small events can have some very big consequences on the macroscopic scale. For example, it's thought that inspiration, brain activity, is related to quantum cascades. So even though you can't see the individual ones, it can have a very major effect. So what do we do? That's why we do it, but what do we do? What does a quantum chemist do in everyday life? Well, I've broken this down into a couple of different things, and I'm using some of the work that my students have done that's represented in posters as explanations. As illustrations. One of the things that we do is sometimes we will use an existing computer program, which is well calibrated, and we know how far we can believe it, to study a specific molecule of interest. An example of that is represented by this poster right here, where we are interested in studying the ground as well as the excited states. The excited states are hard to get, much harder to get experimentally than the ground state of a very important atmospheric molecule. This is the NO dimer. NO by itself is very important, but I think all of you are aware of discussions, for example, of ozone holes and things of that nature, where you have clumps of molecules sometimes, which affects their dynamics. and their longevity. So we can go in there and we can look at some of these, and what it turns out, what it shows, without reading any of the lines, is that some electronic states are stable in the excited states, and some are not. And that affects the chemistry quite a bit. Another type of problem that we do is sometimes we will look at, there's an existing program, but we want to make a high performance version of it. An example of that is represented here in this poster. We have a method, actually one that we developed, called the generalized Van Vleck multi-reference perturbation theory, and we showed it works on some really interesting small molecules. It can handle some tough cases. We can do some exciting things with it, but we always want to look at larger cases, more molecules, more variety of things. And so one of the key, once you know something works, we'll scale it up. And scale it up, including parallelization. This is a student, the first author in this, Rain Lee. She got her PhD with me not that long ago, a couple of years, and she vastly improved the efficiency of it and being able to handle much larger systems. So here the key is things like the speed up, and it's the usual stuff with parallelization, where you increase the number of processors and you know what to speed up, and you measure the speed up, and ideally you want it to be linear, but it's awfully hard to get it linear, but we try to get it as close to linear as we can. So another type of thing is when you are looking for what would the next generation theory look like, and what might the next generation code look like. So what can't we do right now with existing programs, fast or slow? What can't we do? And one of the big challenges for that is something is represented by actually two of these posters. One of them here, where we're beginning to combine looking at the electronic structure simultaneously with relativistic effects. Because here we're looking for, so far we've talked about organic and main group molecules, but when you start getting into the heavier main groups or down into the lanthanides, you have the relativistic effects are very profound. And so how to incorporate relativistic effects within our normal scheme? And what one finds is that there's some very exotic, excited states that occur. This is for molybdenum versus chromium-2. The naive picture of they're just below each other in the periodic table, so they look to be the same, couldn't be further from the truth. Chromium-2 has very weak bonding and a big shoulder on it. Molybdenum-2 has a very deep well, because relativistic effects will contract the S and the D, or will contract the S and the P in general and expand the D's and the F's, and suddenly that shoulder goes away, and you get some very, very interesting effects. Why does one want to do that? Well, things like the gadolinium-2 have the highest spin state of any ground state. Gadolinium-2 is at, it's the 2 times S plus 1, so they have a singlet, doublet, triplet business, has 19½ spin. So that's something that you can't handle with normal software. So we develop theory and do a pilot application to it. Same sort of thing right here. This is one where we're developing molecular gradients, which are very important for considering the change in the nuclear motion as resulted from electronics. And what one does with that is one can look at chemical reactivity. Like, for example, if you're looking at a reactivity of some hydrocarbons with some atmospheric molecules, this is one of the big challenges to get big enough to do it reliably. And this is our suggestion for how to do it. And I know it's very dense it's very dense with equations here. I think the most interesting part is how close can we get compared to what is the exact answer, and we're finding accuracies well within one part in 10 to the 6th on this methodology. And finally, and that's probably what we do more than anything else, this development one. And once in a while we do theory development, actual bona fide theory development, and that's an example from here. And we don't do this very often because it's pretty darn hard to do, but when we do get it, it can produce some very exciting results, and they end up in very high-profile journals like Science, because this can make a profound impact, a broad range of things. The article that we got in Science was based on a type of bonding that's not been observed on Earth. It's based on magnetic bonding, which no electronic effect at all. And it's relevant for how do you get hydrogen, which is the most plentiful element of the universe, from its usual form of hydrogen molecule onto solid hydrogen, which is on like the surface of a star. And so it has to go through some process. And it's not electronic, because electronically it would only be H2. You can't form H2 polymers. And you can't take H2 polymers and form them into H solid. But there is we suggest a mechanism that might do this. Does it work? I don't know. Now comes some good experiments, we made some predictions, but it's a possibility. Those are few and far between. So what I tried to show is sort of a range of things that one can do with computational chemistry or quantum chemistry. My office is at Abbott. Happy to talk to any of you.